First described in 1895 by Emil Fischer, Fischer esterification is a special type of esterification caused by the coupling of a carboxylic acid and an alcohol, typically a primary or secondary alkyl, in the presence of an acid catalyst. Here we have an example of the Fischer esterification process. Beginning with a carboxylic acid, in this case an acetic acid is used, the carbonyl oxygen is first protonated by an H+ ion. Following this protonation, the carbonyl oxygen will now hold a positive charge. The carbonyl carbon holds a partially positive charge in relation to the partial negative charge held by the oxygen. Here an ethanol comes in to nucleophilically add to the carbonyl carbon, which simultaneously breaks the double bond of the above oxygen, thus ridding it of its positive charge. The once carbonyl oxygen is now neutrally charged, and the new substituent that was nucleophilically added holds a positive charge due to its lone pair of electrons. Another ethanol comes in and will deprotonate the OH group at the bottom, neutralizing it. In this step, the OH on the end of the molecule will be protonated, thus creating a leaving group. With another H+ ion, a lone pair of electrons on the oxygen attacks it. An H2O is now formed, and this H2O on the end of the molecule makes a wonderful leaving group. Another ethanol will now come in and nucleophilically attack the top OH group. This deprotonates the OH group, thus creating a negative charge on the top O. Always good to remember your lone pair electrons, kids. The negatively charged oxygen on the top does not like to be in that state, and so finds itself flipping down back into a doubly bonded formation. This simultaneously kicks off the H2O leaving group, resulting in the final product of the synthesis. H2O is a byproduct as the leaving group, and here we have formed an ester via the Fischer esterification process.
The Fischer esterification reaction occurs in wines after they ferment over time. Acetic acid will be present in the solution and will form ethyl acetate when there are excess amounts of acetic acid present in the wine after fermentation. The esterification reaction will then take place with the ethanol. This esterification reaction causes the wine to smell strongly, similar to what nail polish smells like, which is seen as a negative quality of some wines. Chemists have found that this Fischer esterification reaction is acid catalyzed by a hydrogen from either the acetic acid or from a free hydrogen cation in the solution of the wine. Another application of the Fischer esterification to nature is the synthesis of butyl acetate. Butyl acetate is present in some fruits, including apples and bananas, and is largely in part to credit for the flavoring of apples, especially of the red delicious variety. Butyl acetate is created by way of the esterification of butanol and acetic acid and usually occurs in the presence of catalytic amounts of sulfuric acid, also known as H2SO4, under reflux conditions. Butyl acetate is also present in honeybees. The pheromones that honeybees emit when they're startled or scared contains butyl acetate.
There are advantages and disadvantages that characterize the Fischer esterification process when in comparison to other esterification reactions. The main advantages of Fischer esterification are based on its comparative minimalism. Because the reagents used are relatively direct, it poses less of a harmful environmental impact in terms of destructiveness of the reagents, as well as the waste yields that are produced. In contrast, alkyl halides pose potential greenhouse gas issues, or ozone depletion, and other possible ecological poisons. Likewise, acid chlorides produce hydrogen chloride gas under certain conditions, which also result in significant hazards. Fischer esterification is predominantly a thermodynamic process, and due to its slow speed, the most stable ester ends up being the major product. This can be a good thing if there are multiple reaction sites and side product esters to be avoided. The primary disadvantage of the Fischer esterification process also involves its thermodynamic nature. Because of its thermodynamic reversibility, and therefore relatively slow reaction rates, the timescale of a Fischer esterification reaction can be up to numerous hours and even years, depending on the specific reaction condition. In closing, of all the fish in the chemistry sea, there is only one nucleophilic acyl substitution we choose when wanting to produce an ester in an acid-catalyzed reaction, and that is the Fischer esterification.